So the question I chose is from an online textbook. It is a maximum volume optimization question. A sector with a central angle theta over here is cut from a circle of a radius 12 inches. So this is a circle with a radius 12 inches, and this is theta that has been a sector that has been cut out. The edges of the sector are brought together to form a cone as such. Find the magnitude of such that the volume of the cone is a maximum. So for what angle is the volume of this cone a maximum? So I've written down some knowns over here. So what we have so far is here's our circle. The radius is given the variable capital R, and it's 12 inches, but I will be using the variable instead of the constant over here. And the arc length is given their variable x, and the angle is theta. So the circumference is 2 pi r, and we know the length of an arc is the radius times the angle. And we have the cone over here, so the radius over here will be our radius on the cone. And so I just want to point out that the radius of the base of the cone will be given the variable lowercase r, so it's different. We want to maximize the volume of the cone, so the volume here is described as pi r squared multiplied by height over 3. This is the equation we're trying to maximize, our primary equation. Over here in the cone, we can see that the height and the radius of the base of the cone form a right angle triangle. So right away we can use the Pythagorean theorem. We can write that the square of the slant radius is equal to the base radius squared plus the height squared. Immediately we can see that both equations have r squared. We can isolate r squared and plug that back in, so we are only dealing with one variable, being h. So I'm just going to do that right now and rewrite volume is equal to pi r squared h over 3, and r squared from my Pythagorean theorem is equal to our slant radius squared minus the height squared. So I'm just going to plug this in here and simplify to get pi over 3. I'm going to simplify further to get pi over 3 multiplied by r squared h minus h cubed. So we're trying to maximize this equation. So we're trying to find for what height is the volume a maximum. So to do that, we're going to first find the derivative of both sides with respect to the height. So the derivative of the volume with respect to the height. This is our product rule over here. So we know that the product rule is f prime g plus fg prime. So this constant will be our f, and this term will be our g. So if we take f prime multiplied by g plus our f multiplied by our g prime, automatically we know that the derivative of a constant is 0, so this whole term will be 0, so we're just dealing with this term over here. We get pi over 3. Oh, excuse me, this is supposed to be a derivative over here. We'll get the derivative of this with respect to h will just leave us with r squared minus 3h squared. So I brought down the exponent here and got rid of 1 in the power. So this is the derivative of our volume. And we're trying to find a critical point, being our maximum, to find the maximum volume. So we're going to set the derivative equal to 0. So I'm going to divide both sides by pi over 3 here. Grab another sheet. So I can cross out pi over 3. I'm just left with 0 is equal to r squared minus 3h squared. I'm going to isolate for h to get that h squared is equal to r squared over 3. Root both sides to get that h is equal to r over root 3. And I can plug this back into our Pythagorean theorem equation, which was r squared is equal to capital R squared minus h squared. So we'll get that minus, just going to plug that into here and square it. Just to get a common denominator, we'll multiply this and divide this by 3. So we'll get 2r squared over 3. I'm going to root both sides to get that r is equal to root 2 over 3 multiplied by our constant r. Remember, capital R is our constant. So now if we look back at our equation sheet over here, we can recall that our circumference is equal to 2 pi r, and our arc length is equal to capital R multiplied by the angle, and we're looking for the angle. So theta is going to be x over r over here. So our x length is actually going to be, since the base of the cone is a circle and all circles are similar, our x can actually be written as the circumference of this circle minus the circumference of this circle, the base of the cone. The circumference of this circle, including if the x was never taken away, would be 2 pi r, capital R. The sum would be 2 pi lowercase r, but we know that lowercase r is equivalent to root 2 over 3 multiplied by capital R. So we would get x is equal to 2 pi r minus 2 pi root 2 over 3 times r. So we can factor some stuff out and get that 2 pi r is equal, multiplied by 1 minus root 2 over 3. Now we're going to take this equation over here and plug our x in. And as we can see here, r cancels out. This is interesting because we understand that regardless of this length, the same formula would be used to maximize the volume of a cone. So we get theta is equal to 2 pi 1 minus root 2 over 3. If we were to calculate this, we would get that theta is approximately 1.15 radians, which is approximately 66 degrees to maximize the volume of our cone.